All right, boys and girls, I want to quickly go over a couple of the problems that were part of our last homework assignment. They were under the section entitled Numerical Problems from that last set of problems. I had posted yesterday on Saturday the answers to those problems. But in a more general sense, I guess, I want to go over how we name ionic compounds from a big picture perspective. All right. Ionic compounds are made up of pairs of ions. One's a positive ion and one's a negative. I call the positive ion the cation, so there's a positive side, and then the anion's a negative side. And I need to name these ions according to certain sets of rules or guidelines. The cations have their set of rules or guidelines, the anions have their own. Right? If I take as an example, let's take the first problem from number 1 from the homework. It was BeO. Beryllium's the cation, O is the anion. Now, what is special about Be that I know or allows me to place it in the set of guidelines? Well, let's first figure out what the guidelines are. All right, when we're naming cations, we want to watch out for 3 possibilities. All right, the first is that it's a group A metal. All right. By group A metal, we mean that it's a metal that's either in the S block or in the P block. Right? Now don't forget about this little line that goes like this. All the metals are on this side, non-metals on this side. Certainly the first 2 groups are group A metals. There's also a couple of group A metals over on this part of the periodic table. Now, as it turns out, tin, lead, and bismuth, even though they're group A metals, actually are going to get lumped in with the group B's, which are the transition metals. Similarly, there's a couple of transition metals, zinc, silver, and cadmium, that although they're group B metals, they behave as if they are group A's. Right? But more generally speaking, group A metals, the cation name equals the element name. In other words, we don't have to adjust the name at all. So Be is just going to be plain old beryllium. All right. What's another possibility? Well, we alluded to it already. If it was a group B metal or a transition metal, same thing, transition metal, we have 2 ways in which we could name these guys. One is called the stock system, and this uses Roman numerals. Or B, the classical system. And I had given you notes or lists of these group B metal ion names, so dig those up. All right. Classical system uses an OUS or an IC suffix on the name of the ions. For example, if this happened to be FeO, right, if it were FeO, well, Fe, as it turns out, is part of this, the group B metals. So I would have to call that, as it turns out, either iron 2 oxide, right, the O's oxide, either iron 2 oxide or iron 3 oxide. Now, I'm not going to get into detail about how we do that right here. We'll do a few examples. And then lastly, for the cation half of things, there's one last possibility. And that is if it's a polyatomic cation. And for our purposes, we are going to run into one and only one of these. All right, on this list of polyatomics I gave you, it's right at the top. All right, you want to look out for something that has the formula NH4 right out in front. So it would be NH4O, for example. What is NH4? It is the singular polyatomic cation with a +1 charge that we need to know. And its name is the ammonium ion. Right? So when I'm looking at the formula of an ionic compound, right, let's go back to that BeO example. Be is either number 1, a group A, number 2, a group B, or it's ammonium. Well, definitely not ammonium because Be is not NH4. Is it group A or group B? Well, that depends on its position in the periodic table. Be is in the first 2 columns, so it's a group A. So for group A, I name the cation the same as I name the element. So Be is beryllium. So the first half of the name of this compound is simply beryllium. All right. What if it were FeO? Well, we have 3 possibilities. Either it's a group A, a group B, or this ammonium ion. Well, it's certainly not the ammonium ion. Fe is right here. That's a group B, so it falls into this category, which means that I can't just simply name this iron oxide. I have to either use a stock system, which is going to include Roman numerals, or a less used system, the classical system. Right? Now, in this particular formula, FeO, turns out this is iron with a +2 charge. And hence, we would use the stock system. We would call it iron 2 oxide. All right. Now, how about if the formula was NH4Cl as an example? Well, if you see a formula starting out with NH4, you immediately call it an ammonium compound. So this is going to be ammonium and then whatever the Cl, in this case, is chloride. This would be ammonium chloride. All right, let's take a look at the back half of the compound. All right. When we're looking at the back half of the compound, all right, we're going to run into only 2 possibilities. That it's a group A nonmetal, right? And by group A nonmetal, I'm talking about these guys up here in this corner of the periodic table. As a matter of fact, all the nonmetals are group A's. All right. And when we see these as part of a compound, let's go back to the NH4Cl. All right. The Cl is the back half of the compound, the anion. It is a group A nonmetal. The name of the element gets an IDE ending. Name of element gets an IDE ending. So this guy would be ammonium chloride. All right. Now, the other possibility on the negative side of the compound, part 2, is if it were a polyatomic anion. Now here is where the vast majority of the polyatomic ions are. They're all negatives, well, except for the ammonium, which is positive. But there's a whole list of -1 ions, a whole list of -2, a couple of -3s, and then there's some -4s and -5s. But you really just need to recognize on the anion side if it's polyatomic. Okay? How do I recognize if it's polyatomic? Well, the word poly means many. All right. In this example with the chloride, there's only 1 element listed there. So that's not many elements, it's only 1 element. All right. These are known as monatomic ions. We're looking for the polyatomics. For example, what if this were NH4ClO3? Well, the NH4 part's the positive half. The negative half is everything else, the ClO3. Well, I see a chlorine and an oxygen here. That's not a single element, that's more than a single element. Therefore, I make the conclusion that it's polyatomic. Poly means 1. More than, poly means many. All right. In this case, it's going to be more than 1 element in the ion. So if this were my example, I see chlorine and I see oxygen is automatically polyatomic. And what do we do for polyatomics? You just look for them on the list I gave you. Okay. So, in this case, if you look up the ClO3 ion, ClO3, it's going to be, where is it? ClO, there's ClO2, ClO4, where's ClO3? There it is, ClO3. It's known as chlorate. So this would be called the ammonium chlorate compound. All right. Let's go ahead and look at the next problem here. All right, it's going to be Pb and then OH taken 2 times. All right, that's this one right here. Now, Pb, as it turns out, happens to be, although it's a group A metal, it really behaves as if it's a group B. So I'm going to go down here to this. For the group B metals, I'm going to have to use either the stock system or the classical system for naming this. Well, the stock system utilizes Roman numerals, which indicate what the charge on the ion is. So these are really the hardest problems of all of these, is because I don't know what the charge on lead is without doing a little bit of figuring out. What I do know is that the lead's charge balances the anion half of the compound's charge. So we have to look at the anion to determine what lead is doing. Let's look at the anion. How many different elements does it contain? Well, it's 2. So that's going to be more than 1. That's polyatomic. Just look it up on the list. All right. OH. Where's my list? OH. Look it up here. Here it is right here. OH. And it's got a -1 charge. And it's known as the hydroxide ion. So this is going to be lead something hydroxide. Remember, for the lead, I need a Roman numeral. All right. Now, in this particular case, let me do it right here. Pb and then OH taken twice means I have 2 OHs, each of which is a -1. Now, if I have 2 -1 charges, then the lead has to balance that, and the only way it could balance it is if it's the lead 2 ion. So I'm going to call this guy lead 2 hydroxide. Lead, and then Roman numeral 2 hydroxide. All right. Now, if we go back here, the other way we could name these is using a classical system, which means that it's going to contain an ic or an us suffix. And on one of the other ion sheets that I gave you, if you look up the names here, lead 2 is known as plumbus. So another name for lead 2 hydroxide would be plumbus. Lead 2 hydroxide is plumbus hydroxide. I'm not going to write that out again. All right. What's the next one? Let's go to letter D, Na2Cr2O7. Na2Cr2O7. All right. Where do I break this in half into a cation side and an anion side? Well, if you look at all our possibilities for cations, the first ion is almost always going to be a monatomic ion, except if it's ammonium. Now, this is not NH4 out in front, it's just Na. So that means that this must be my metal portion, my cation portion of the compound, and everything else is the anion half. 99 times out of 100, if you separate this formula into 2 halves, where the first half contains just the single element, then the rest of it is going to be the anion. All right. The only time that we have to concern ourselves with something more than one element as being the cation is when that cation is specifically NH4. All right, so Na, what is it? A group A or a group B? Well, it is a group A, which means that the cation name is the same as the element name. So this is going to be sodium and then whatever the name of the anion is. All right, what about the anion? All right, well, there's a chromium and an oxygen being listed here, so that is definitely polyatomic. How do I name polyatomics? Just by looking them up. And so get out your polyatomic ion list, Cr207, it's going to be right here. Cr207 is known as dichromate. So this guy is going to be called sodium dichromate. All right. And we'll do letter G. Na. And then there's an H2PO4. All right. Where can I slice this formula into a positive half and a negative half? Again, all of the possibilities for positive cation possibilities is if it's a group A or group B metal. So it'll be just the symbol of a single metal element. The only other case we'd run into is if the cation were polyatomic, but very specifically only the ammonium ion is what we're going to run into. All right. And we definitely don't have the ammonium ion here. It's just Na. So we're going to divide it in half right between the Na and then the rest of the compound. Na is a group A metal, so the cation name is the same as the element name. So it's just going to be plain old sodium and then whatever the H2PO4 thing is called. This whole group of elements and subscripts, element symbols and numbers, is one single ion. We just have to figure out what it is. All right. And if we look around on our sheet, H2PO4 is right here. It's called dihydrogen phosphate. So this is going to be sodium dihydrogen phosphate. And that's it, boys and girls. I think this little set of notes right here might be a good thing to maybe put down in your notebook. I'm going to be sending out your quiz for this topic on Monday. And it's on a Google form. It's all multiple choice. It'll be due by the end of the day. And hopefully this might be of some help to you. All right, that's it.